Grade 12 Physics, Energy and Momentum, Note number 1. This note is about work and energy. It'll be a review from grade 11. So essentially, we'll start looking at work. Work is defined as the amount of energy transferred by a force over a displacement. So if we use a force to move something, there's a certain amount of energy transferred which we call the work done. It can be calculated if we multiply the force with the displacement of that object, where work is in joules, force is in newtons, and displacement is in meters. Now, it's not necessarily a direct multiplication between the force and the displacement vector. It's actually something called a vector dot product. So for a full efficient work to happen, we need force and displacement to be pointing in the same direction. If they're not, we have to take that into account. And there's an alternative form of the formula where the relationship between F and D can accommodate an angle between them. In this case, work will be equal to F times D multiplied by cos of that angle between them. So moving on, there are more conditions according to this dot product. Specific conditions when we might get zero work done. The first one is when force is perpendicular to displacement. So that's when, if we take a look at that formula, W equals FD cos theta, cos 90, which would be perpendicular, is equal to 0. So that would give us no work done. Next condition would be when force is equal to 0. That would give us no work. And also when displacement is equal to 0. That's also equal to no work. We might also have negative work. So that's basically any situation where the force is pointing in the opposite direction of the displacement. So this is any case where you might have something slowing down. You'll have a forward displacement, but if you're putting on the brakes, then you have a force in the opposite direction. So really, that force is doing work to take energy out of the system. You're losing kinetic energy. So this leads up to the next statement down here, which would be the work-energy theorem. This is a central component to how work and energy are connected. Any work done to a system equals its change in energy. So if you throw a football forward, you're doing work to it to speed it up. That work that you do is equal to its velocity afterwards. Equal to its kinetic energy afterwards. Same with lifting something. If you lift it, you change its gravitational potential energy. So the work done is equal to the change in gravitational potential. So let's look at an example here. Let's say we push a cart around in a circle. The circle will have a radius of 5 meters. And let's say we put a force of 12 newtons on that cart. Let's try and calculate what the work would be after half of a lap. So if we take a look what that looks like, sure, we're going to go out on the outside of the circle, but work really depends on that displacement. And all displacement cares about is where you start and where you finish. So we'll multiply 12 newtons multiplied by the displacement, which in this case will be double the radius. It ends up being 120 joules. If we take a look at after a full lap, here we're basically ending where we started. So our displacement is 0. So if we put that into our calculation, where displacement is 0, we get no work done. So we need to pay attention what our displacement is to actually calculate our work. Let's also say maybe we're mowing the lawn. So if we draw a picture of a lawnmower here, we put a force, we'll push down on the handle of the lawnmower, which ends up being about 15 newtons. But we move the lawnmower forward with a displacement of 8 meters. So here we have a 30-degree difference between our force vector and our displacement. We have to use the alternative form of the formula. So here 15 times 8 times cos 30 ends up being 104 joules. Final part of the review from grade 11 here will be a review of energy. So we need to remember that in a closed system, no energy is gained or lost. If we look at a system at the end versus the total system at the beginning, the energy before equals energy after. And we denote that energy after with a prime or a hyphen on that last E. If work is done to the gain or lose energy, we need to accommodate for that. So if work done where we add energy to the system, it's plus W. If work is done where we lose energy, like slowing down, it's minus W. And we'll use our same energy formulas from grade 11. Kinetic energy is 1/2 mv squared. Gravitational potential energy will be mgh. And we also looked at thermal energy last year, which would be mc delta T. So let's do one example here before the note's done. Let's say a soccer ball, which is about 0.43 kilograms, gets kicked down an 18-meter hill. If it was kicked with an initial velocity of 7.4 meters per second, let's try and calculate our final velocity using energy analysis. So it's important in these questions to organize our thinking. We need to make sure we know what's before and what's after in our equation and what the variables are for each. So let's look at the h, the m, and the v initially and finally. Our height changes. We start from 18 meters and we go down to 0. Our mass does not change. And finally, the velocity does change. It goes from 7.4 to something else, and that's what we want to calculate. So energy initially equals energy finally. Let's consider gravitational potential and kinetic on both sides, initial and final. Here, because we have a final height of 0 meters, our final gravitational potential energy will go to 0. Also, there's an m in every term, so we can divide through and cancel that out. Now let's just insert our numbers and do the calculation, and we find that our final velocity will be 20.2 meters per second.